automatically you know that there's going to be a helium ion produced as a product. And now what we're trying to figure out is what is the other unknown molecule. So this is how we do alpha and beta decay questions. So law of conservation of matter tells us that you have to, so if I have a mass number of 241, I have to have a mass number of 241 over here. So this is algebra. Right, so what I'm going to do for the top here is it's going to be 241 equals 4 minus A. Sorry, or 4 plus A, right? So 241 minus 4 equals A. So that will be 237. All right, so I know that this is 237. Okay. I've taken 2 protons away, so this is going to be 93. And when I look on the periodic table, X, this makes, so I have 93 protons, right? Because I have to have 95 on both sides. That's neptunium. So my unknown is neptunium-237. Okay. All right, so let's look at page 506. I'll do a couple questions here. 29. So A. So it says, write the balanced nuclear equation showing the alpha decay for each isotope given. So this is beryllium-8, so Be8. And it decays, so beryllium is decaying. What we know about beryllium, if I look at my periodic table, it has an atomic number of 4. So this is Be4. It's a beryllium-8 isotope, and it alpha decays. So that means it makes a helium ion, or helium atom. So I need to account for the rest. So I need to find out what this is. And, right, you know that this is half of both of these, so I'm going to end up with my unknown being another helium atom. Okay. I'll look at B, and then I'll leave C, polonium to U. Uranium-232 is going to alpha decay. So we have uranium-232, and remember, I'm going to go back on my periodic table, and uranium has an atomic number of 92. And it's going to alpha decay, so it makes a helium atom. So I've accounted for 4 nucleons, so there's 228 left over. And then this will be 90, and then I have 92 and 232 on both sides, right? So that's going to be thorium, 90. Okay, that's how I do alpha decay. Okay, so if I look at number 30, it says each of the following atoms is a product of alpha decay. Write the balanced nuclear equation for each. Okay, so you have to work backwards from this. So alpha decay always produces a helium atom, and one of the other products is uranium-230. Actually, I'll do B. You can do A on your own. So plutonium is the other product. So this is 236. Plutonium is Pu, and it is 94. Okay. So I just added up to see what the reactant is, right? So 240 is the amount of nucleons, and then 96 is what's on the other side. So when I find that out, it's curium, named after Mary Curie. Okay. So that's how you do that. Okay, so that's alpha decay. Beta decay is another thing that you do need to know as well. So this says beta radiation is a stream of beta particles emitted from unstable nuclei. A beta particle is a high-speed electron. So what happens here is when an atom destabilizes and beta decay occurs, a neutron is converted to a proton. So something that's neutral turns into a positive ion. In order to balance that charge, an electron is also produced. So during beta decay, the number of nucleons does not change, but the atomic number does. So what happens is the atom moves up the periodic table because it creates a proton. Okay. So beta decay. So this is page 506. Okay, this shows what happens. So the charges need to balance, right? And so if I look at, so page 506 and 507 have practice examples of beta decay for you. But I'm going to look at 32 and 33 on page 507. Okay, so it says each isotope listed undergoes beta decay. Write a balanced nuclear equation showing the change that occurs. So we have krypton 87. So this is Kr87, and it's actually going to produce a beta particle, which is an electron. So it doesn't have a mass, and it has a charge of -1. So that's -1 positive charge. So krypton on the periodic table. I always need to find this one. Here it is, krypton. So it's a noble gas, 36. So it has an atomic number of 36. Okay, so what happens is the mass number doesn't change, okay? Because the electrons don't have a mass, so whatever the product is still 87. But in order to account for having 36 protons on both sides, the molecule moves up the periodic table. So 37 is rubidium. So beta decay of krypton will produce rubidium. Okay, you can do 32b on your own. 33 says each isotope is listed as a product of beta decay. So this is the same thing as the other series of questions. Use a balanced nuclear equation to determine the identity of the isotope. So I'll look at nickel. So 33b. So what we produce nickel 60. So nickel 60 was produced as a product of beta decay. Nickel is number 28. So it has an atomic number of 28. So mass number is going to be the same here. Okay, 28 minus 1 is 27, so this one has to be 27. So my parent material for this reaction is cobalt. Okay, so that is beta decay, where we produce an electron from the breakdown of a nuclear atom. Okay, gamma radiation is also something that's produced from nuclear decay. There's no mass or charge. It'll be produced in conjunction with alpha and beta decay. So you'll see it as part of a product, but it doesn't have any effect on the math. You'll just see it in there. And there should be... This is how you'll see gamma radiation. So gamma, if gamma radiation is produced, you'll see it as a product, and you'll see it as this gamma sign. Okay, and that's on page 508. Okay, page 509. Also, questions number 34 and 35. This also addresses beta decay and alpha decay. And you just have to add the gamma radiation in there as a product. Okay. So when we look at alpha decay, that's how atoms they change state over time, and that's how we get half-lives, and we can age rocks and things like that. If we actually want to split atoms right away, we can use fission to produce energy. What we want to use is fusion, but we can't do that on Earth right now in any sustainable form. Fusion is the main energy source that fuels stars. So nuclear fission is what we've been able to do, and this is what creates atomic explosions, right? So nuclear bombs. So nuclear reaction in which a large nucleus splits into smaller nuclei is nuclear fission. Atoms are split to release nuclear energy. So what we need is we get a massive amount of energy release. But what we need in order to do this, to create a chain reaction, is a critical mass. So we have an isotope of a heavy element that is knocked into radioactive material, and it creates a chain reaction that destabilizes atoms. So you need a critical mass of a heavy isotope to do that. Right, so if you have an ideal amount of a large nucleus, a neutron smashing into the mass of atoms can spark a chain reaction. So this is critical mass here. Okay. So if I, pound a uranium atom with a neutron in the right spot, it will create this successive amount of radioactive decay. Okay. And this is fission. And this is what we do in nuclear power plants and nuclear bombs. And then, and the destabilized atoms will destabilize other uranium atoms. So if we have uranium in a high enough concentration, right? So weapons grade uranium is a certain concentration of uranium in a certain area, over a certain area, then we can create nuclear explosions. All right. Okay, so this is a fission reactor. On my slides. So fission equations, a large nucleus such as uranium is struck by a neutron, and the neutron breaks the atom into two products. A lot of energy is released in this process. But in a nuclear reactor, this energy is transferred as heat to water, and this can be used for energy. So fission equations works on the same principle as alpha and beta decay equations. Page 511, I'm going to look at number 36 here. Okay. So this says the fission of uranium-235 can produce many different products. The following equations show one product of the fission of uranium-235. Use a balanced nuclear reaction to determine the unknown product. Okay, so A gives us uranium-235 as a product, and we're going to smash a neutron into it. Okay, no protons in a neutron, obviously. So my total mass number is 236 on the reactant side. And then that makes 3 neutrons plus an unknown plus an iodine isotope. Okay. All right, so here's the deal. I have a total amount of mass number of 236 on this side. I've got 3 plus A plus 137 on this side. Okay. So, this has to equal 236. Right. So, if I have 137 plus 3, that's 140. So, I know that A is going to be 96. And I just figure out the difference. Okay. We have 92 protons on this side of the equation. So there has to be 92 protons on this side of the equation. So this is 3 times 1 neutrons, by the way. So that's why I have that 3 there. So there's 53 protons accounted for. So 92 minus 53 will give me how many I need to have with X. So 12 minus 9, right? So that's 39. So my element that's produced through this reaction then is yttrium, or Y. Okay, it's number 30, has atomic number 39. So that's how I solve fission equations. All right, let's look at B. B says, I've got uranium-235 with a neutron smashed into it again. And we make bromine this time, plus an unknown. Okay, so this is uranium-235. Neutron, we get a critical mass of uranium to spark a chemical reaction. 3 neutrons. Plus unknown element X. And then we get bromine 90 isotope. Okay. So again, 236 on this side, and then this is going to be 3 plus A plus 90. So we have 93 nucleons accounted for, so we need 143 remaining. So my A is going to be 143. There's 35 protons accounted for here, right? So 92 minus 35 will let me know how many protons are needed here, because I have to have 92 on both sides. Okay, so that should be 57. And so this is an X143 isotope, but 57 is lanthanum. So this is a lanthanum 143 isotope. Okay, and that is nuclear fission, alpha and beta decay. Okay, how do we control fission? Right, because the reactors can melt down if we don't control it. So the fission of uranium-235 in a nuclear reactor requires a constant stream of neutrons. So we have enriched uranium to provide nuclear reactors, right? So we actually have the nuclear reactors are in uranium dioxide pellets. Actually, a lot of uranium comes from, so we bond the uranium with oxygen. A lot of uranium comes from Saskatchewan, actually. Sections of the rods are exposed to neutrons to undergo fission. So we don't expose the whole uranium rod. We'll kind of open up parts to smash neutrons in. And then the uranium rods are held in deuterium, so heavy water. So water with an extra neutron. And that keeps the, right, it slows the speed of the neutrons and helps us control, right, when the neutrons smash the uranium pellets. And it helps us control the rate of reaction in a fission reactor. All right, so these are uranium fuel rods, uranium dioxide pellets, and they're open at certain gaps, and we'll smash neutrons in at gaps. And then this is an example of a fission reactor with deuterium that is controlling the reaction. So it looks kind of space age, but it is nuclear physics after all. So this is what happens, right, when we don't control. So if the uranium rods overheat, they will melt down. So the critical mass will be uncontrolled, and you'll have an explosion. So this is what happened with the Fukushima reactor in Japan after the tsunami. Right, Chernobyl was another nuclear meltdown. This is why there's concerns about nuclear power as we try to green our energy. Right, nuclear power produces no emissions; it's very clean. But if a reactor melts down, the consequence is catastrophic. Right, and so so the Fukushima reactor contaminated soil from about 10 square kilometers away, and it's still leaking today. So radioactive waste is being leaked into the Pacific Ocean right now. We haven't been able to control that. So improper control of a nuclear reaction, right? Okay, we'll talk about fusion, and we'll talk about E equals mc squared in the next lecture here. I'm going to sign off and post this one, and then finish up with the course content in Science 30 in the next lecture. Bye now.